All right, good morning, everyone. Welcome back to um, this discussion of equilibrium. And I want to point out, or I want to draw your attention to what I said at the very end of what I said at the very end of last lecture. These procedures and examples, these are super helpful. Okay, so I would highly recommend that you go through those examples starting on page 696. Actually, there's a bunch of examples throughout this entire chapter that are quite useful, but these in particular are very useful. And so I highly recommend that you go through these, work through them, and if you do that, I think that it will be a lot easier for you to understand the process of the ice table or solving for equilibrium concentrations, etc. Okay? So, we went through some examples last time where we used the quadratic formula and we had to solve for x and all this. Now, there are some very useful approximations that you can make, okay, within this solving process. Turns out that when k is very small, okay, we can assume that x is much less than a initial. Okay. Now let's think about this. If we have a reaction that starts with A and, for example, goes to 2B, our favorite. There shouldn't be concentrations around that. Goes from A to 2B, our favorite generalized chemical equation. If we have some sort of initial concentration of A, let's say 1.0 molar, why not? And we have some initial concentration of B, 0.0 molar, right? Now, let's say that our K is very small, so in this case, 3.3 times 10 to the minus 5, okay? In our example here, K is quite small, very small. We can assume that X is much less than A. If we look at an ice table, this becomes apparent as to why. So let's have our concentration of A on this side and our concentration of B on this side. If we start out with 1.0 and 0.0, we have minus X and plus X. Now remember, the equilibrium constant tells us how much the reaction goes towards the sorry, my kid just walked in the room. Hazel, no. Hey, you gotta go out, huh? I'm doing a lecture. Can you go find mommy? Go on. No. Yeah, don't worry about it. Okay, sorry guys. Sorry about that. Yeah, Hazel just walked right in to the room. I forgot to lock the door this morning. Okay, let's continue. So we have this amount of A that gets taken away from A, negative X. That's how we represent it. Now, if we remember what the equilibrium constant actually is telling us, it's giving us the amount of products that we have divided by the number of reactants. In this case, since it's very small, that means that both the reactants are very large. The concentration of reactant is very large, so it's dividing by something large. And the concentration of the product is quite small. Okay, so that's what X means. That's why we can say that X must be very small or X must be much less than A initial when equilibrium constant is small. Now I made a mistake here. I put in just plus X. It's plus 2X for B. At equilibrium, we have 1.0 minus X and 2X for B. We can solve for the equilibrium constant as B squared over A. is equal to 2x squared over 1.0 minus x is equal to 3.3 times 10 to the minus 5. Okay, so far we haven't actually used this assumption. Okay, we're still just solving it the normal way that we always do. However, at this point we can start to say something about this assumption. This part here, 1.0 minus x. That is a initial minus x. A initial minus x. So, since x is much smaller than a, well, let's make it an if. If x is much smaller than 1.0, then 1.0 minus x is approximately equal to 1.0. Okay? If you take away a very small number from 1, you're still going to have approximately 1 in terms of the amount that you have and in terms of the significant figures. So we can simplify this whole thing to 3.3 times 10 to the minus 5 is equal to 4x squared divided by 1. You can see how much that simplified this problem. We don't have to do the quadratic formula at all. We can directly solve for x. And in this case, x turns out to be equal to the square root of 3.3 times 10 to the minus 5. If I just solve this bit, that's what I get, over 4. And it turns out that x is equal to 0.00029. Oops, too many zeros. 0.029. Okay. Now, this is what we find for x. We have to, at the end of making this assumption, we have to check the validity of the assumption. Okay, we have to check this. If it doesn't make sense, this check won't work. So, for example, if we have x over a is equal to, or let's make it times 100 here. If x divided by a times 100, so essentially I'm looking at a percentage of this, okay? If x over a times 100, 0.0029 over 1.0 times 100 is equal to 0.29%, okay? This value here, if the percent is less than 5%, then the assumption that you make is valid. Okay, so if you get to the end and you find that x is less than 5% of a, then you know that your initial assumption is valid. Okay, so if this falls below 5%, you're good and you can make that assumption. If it doesn't, then you have to go back and use the quadratic formula to solve for x. Though not harder, but a little bit more complicated, and it takes a little bit longer way. Okay. There are, just like there are examples on page 696, there are more examples for this assumption on page 700 and continuing. I highly recommend, again, that you go and look at these examples. They're extremely helpful. They're all worked out in the book. They're pretty easy to follow, and they'll show you exactly what you can do in each and every situation that you might come in contact with in an equilibrium problem. Okay. So, moving on. We have gotten to the point where we can now talk about not only equilibria and how they reach equilibria, and how to calculate the concentrations and constants at equilibria. What we want to talk about now is what happens when you have an equilibrium and you disturb it in some way. Okay? This is answered by something called Le Chatelier's principle. And I promise you I am not making this name up. Le Chatelier, French dude, obviously. French dude. And he sought to answer the question of what happens when an equilibrium is disturbed. What do I mean by when an equilibrium is disturbed? Well, say you have some equilibrium between A and B in a flask. You've reached some equilibrium concentration. You started out with 1 mole of A, and now you have some equilibrium of A and B together. Okay? Now, say that I had a way to get rid of some of the B that I've produced by this reaction. What happens to the equilibrium? Well, suddenly I'm taking away B concentration, and so the entire system must react to that disturbance. So the Le Chatelier principle, which I affectionately call LCP, the Le Chatelier principle states that when a chemical system at equilibrium is disturbed, the system shifts in a direction that minimizes the disturbance. Okay? The system shifts in a direction that minimizes the disturbance. Now, what does that actually mean? Well, we have to talk about what the disturbance is actually coming from, it turns out. So how are we disturbing the equilibrium? There's several different ways that we can do this. We can do this by changing the concentration. We can do this by changing the pressure of the system. We can do this by changing the temperature of the system. Okay, so let's go through each one of these different changes or possibilities and talk about them individually. Okay, and we will do that in part 2. So I'm going to end part 1 here. Take a break, stretch your legs, get some snacks, and yeah, we'll be back here in just a little bit.